Hi, I'm Jason Natale. I'm going to be presenting research done by Juan Dang and Vincent Conitzer from Duke University titled Disarmament Games. They're exploring why optimal outcomes sometimes aren't reached in situations where you have multiple governments, people, or companies interacting with one another. One of the main reasons for this is a fear of lost leverage. Neither party wants to be the first to reduce one of their dominant strategies because they fear they will be left vulnerable to the other's interaction and decision. At the same time, externalities come into play. Very often, these agents aren't making decisions based on how they will impact everyone else. They simply care about their bottom line, their utility. To begin analyzing and evaluating these scenarios, it helps to formulate them as a game. Here you see the classic prisoner's dilemma game, where you have two prisoners with the choice to either cooperate or defect from their situation. The boxes show the utility values for each prisoner, one being the row player, one being the column player, per decision set that is made. This game is heavily popularized because of the fact that a Nash equilibrium resides in the defect slot, which is a suboptimal outcome because each prisoner would only receive a value of 1. The disarmament game builds on top of this normal form two-player game. It has a directed acyclical graph which represents the game tree. In this game, players alternate in reducing their strategy space. Some questions posed by our researchers are: 1. Can a disarmament solution arise? In other words, is there an equilibrium of the disarmament game which leads to some desired specified outcome? The next question, one being a little bit more specific, is K-disarm, which is essentially asking, can this specified outcome be reached in only K rounds of disarmament? When talking about rounds of disarmament and the game tree which I mentioned earlier, it's important to note that the path of the game tree between two nodes is the same thing as rounds in the game. So when they mean K rounds, they mean a K length path of non-terminal nodes. The last question is, what are the complexities of these two problems listed? To start in answering these questions, we need to list a few definitions. First is the game strategy profile. Sigma 0 and Sigma 1 represent the strategies of player 0 and player 1. Further, a strategy of player B, Sigma B. This consists of an alpha and a beta. The alpha is the disarmament strategy of the player. This is the Cartesian product of any non-terminal node H in the player B's move chosen. Next is the play strategy beta. This is the Cartesian product of any terminal node and the set of distributions over T of B. U sub B given O is player B's utility for an outcome O. The on-path history P is represented as H of 0, which is the root, all the way through H of K plus 1, which is the terminal Z node, where all i's satisfy the successor function, which maps non-terminal nodes and the agent's disarmament strategy to a successor node. Some terminologies which also need to be known for this research is strategic dominance. Strategic dominance is a situation a player or an agent will have when one decision is by all accounts better than any other decision they could make. That is, that the one decision given any of the other players' decisions gives them an optimal value. Secondly, we have Nash equilibrium, which is a stable state whereas neither player can improve their utility by making an adjustment to their strategy or an adjustment to the decision they have made. Lastly, and this is specific to the research done at Duke University, is a concept of security, which is, given the action sets T of 0, T of 1, this is the utility which can be derived at the very least to a player B. The minimax theorem is used to calculate this. Taking a closer look at our disarmament game, we see the individual states, the relationships between them, and the stages at which player 0, player 1, player 0, and then in abstract terms, player B makes their decision. Each non-terminal node in this directed acyclical graph has three main components: the strategy space of player 0, the strategy space of player 1, and the player making the move at that time. For the terminal nodes, only the two strategy spaces comprise the game state. Between game states, a player can choose to either pick some discrete subset of their current strategy space, represented as x0 or x of 1, or they can choose to play the normal form game which exists currently between those two strategy spaces. In the pure strategy version of the disarmament game, discrete strategies must be removed one by one. There is no mixing strategies. The security of a given strategy for an agent B, given the strategy space T sub 0, T sub 1, must always be less than or equal to U of B, given the outcome O, if that outcome of O is to be achieved through a Nash equilibrium. We can prove through the aid of the minimax theorem that this can actually be achieved along a path with a Nash equilibrium strategy profile. The on-path history of this would be big O of the cardinality of S sub 0 plus the cardinality of S sub 1.
This can be used as a polynomial length certificate for verification of the disarm and k-disarm problem. By reduction of the balanced vertex cover problem, we can also prove that disarm and k-disarm are NP complete. This is calculated by giving separate utility values for remaining edges and vertices after the balanced set of edges and vertices is reduced to some limited set. A mixed strategy formulation of the game was also presented by our researchers. Here they set an upper bound for some suboptimal outcome and reduce that upper bound with each step along the game. This reduction was a factor of k if some probability delta occurred on each step. This probability delta was needed so that neither player would actively choose to make this decision, but rather they understood there was some external force, or some external probabilistic force, that is, making this decision. The utility of some player B after their strategy space has been reduced to k of t can be quantified in the equation shown. This equation assumes that our game could go on for an infinite number of turns. Our researchers also proved that with this infinite length turn game, there is also convergence to an optimal outcome. It should also be noted that this infinite turn game presented itself as they took their delta value, their value that the game would suddenly stop and each player would have to play the remaining normal form game. This delta value was brought lower and lower until it converged to 0. A folk theorem was developed for our mixed strategy game to prove some sort of efficiency for a limited number of turns. Given the update function f, which calculates a possible coefficient for a suboptimal strategy space, given that the security of the next player will be less than or equal to the utility, the optimal utility of the next player. Forcing the security value to be less than the optimal utility value makes sure that the other player stays on path to full disarmament. The algorithm for this can be seen on this slide. With an infinite loop, as long as this coefficient remains higher than the next update function's coefficient, the players will continue to alternate, the turns will continue to add up, and new non-terminal nodes will be found. This folk theorem proves to us that for mixed strategy games, convergence to being within big O of n over t of some optimal outcome can be achieved in a finite number of turns, specifically t. Further exploration, as suggested by researchers, includes examination of other representations of games, and to look for other solution concepts besides the Nash equilibrium, which can be solved via disarmament or some disarmament-like system. Methods of reducing the strategy space besides putting upper bounds is also something that's recommended to be examined. Another thing researchers could possibly do would be to design algorithms that would work well in the real world, working with real companies and real governments to achieve these optimal scenarios.